So then another example, 41, which is a bit more interesting, is logistic regression. And so I'll just introduce what that is because it's going to come up again later, and it's kind of related to other stuff if you haven't seen it. So logistic regression sounds like linear regression, but it's not actually regression. It's actually classification generally. So they have the same idea. You're basically defining a probability distribution over some data and some weights, which are parameters, right? You can use a theta if you want to call them theta, and your outputs. But in this case, we want to actually pick a label, right? So we want to pick about whether this value, this y, has a particular label or not. And it's giving us a distribution, so a probability of that label, of that value being having the label, right? So you have your images of cats and dogs, and you want to work out if this image has a cat or a dog in it, y would be cat or dog for each individual image you've got. You're basically, it'll return you a probability of it, that data point being in the class that you asked it. But the logistic kind of function on its own is this. I have that on the next slide. So that's the overall method. So it's we can call them both linear and logistic regression. Both are generalized linear models because they have a linear, basically combination of the data with some weights and noise. But the function that we're pumping it through for logistics is different. Because it's this this function, which has that form 1 over e to the minus weights plus the sum of the weights, and you get this logistic or sigmoid function. So in the early days of neural networks, which we'll talk about when we get to that, this was used in one of the core components in the middle. It has this useful property that you can give it inputs, any number of the input values x can be any number, and the output's going to give you something between 0 and 1. So essentially it's normalized to give you a probability, but it's not linear. So it has this kind of sigmoid shape. It's not S. People liked it for neurons initially, for, well, I actually have the picture on the next slide, I think, for neural networks, because the idea is that somehow like a synapse in your brain builds up and builds up information, builds up sort of responses, and then at some point it hits a threshold and it goes up to another value. So the fact that it's slow building and then it switches kind of more dramatically to another one means that it's nice for having as a threshold, right? So if you set your threshold for classification somewhere here at, what did I set it to, 55%, then any values that are above this might be in the class, and any values below it would be not in the class, right? So that's kind of the idea. And since it's got a dramatic change in the middle, it's good for that. Or at least everybody thought it was. They actually found better ways to do it afterwards. But for logistic regression, that's all it does. It has basically just this function. We have this other term, W, so there's a starting value, which is called the bias. It's different than the bias we talked about yesterday. It just gives you the offset here, so if the bias changes, it moves this left or right. And the other weights affect how this curve, what steepness it has, given the data, right? And so that idea for like neural networks kind of comes from this way of thinking of it, that you have a bunch of input data that comes in to a sigmoid unit, and you sum them together with these weights, and then you pass it through this nonlinear function, sigmoid, and you get some predictor output of that value. And like we said, you can threshold it and say, well, if the probability is above 70%, it's in the class or not, right? So it's a very simple idea. Logistic regression just uses this. What's the next slide about that? So it's a very simple method, and it's easy to fit, but they don't fit it analytically the way we do with linear regression. They fit it using gradient descent. So they kind of like choose the values of the weights, and they kind of adjust them to improve the value. So when you look at the parameters, you can compute the parameters saying like what's the probability of y having class 1 versus y having class 2, and then use this ratio. And so the parameters that you're looking at, the weights almost have a bit of an interpretability that they're like the log odds, like given this data point, how much more likely is it to be in the class versus not in the class, if it's just a binary classifier. So they have a little bit of interpretability, which is nice. So the data set here, we had cigarettes per day, if anybody smokes anymore, the number of cigarettes someone smokes per day, and then you have two different variables, different features, how much exercise they do, and then the label was whether you get lung cancer or not. And then if you learned these parameters, 1.3 and minus 1.1, it means that the log odds of each cigarette raises your kind of probability of, well, your odds. You get e to the 1.3 times more likely to get cancer every time you smoke a cigarette, and you get, e to the minus 1.1 times less likely every time you go out for a run, right? So you can kind of interpret them that way a bit. The way that it's kind of used a bit more is like what I said, where you have essentially a line that you're drawing through space, and then what you're fitting it using this logistic function, but still a line through space. So if we had two-dimensional data, like the smoking data, we'd fit this line, we could just plot it, and then we're essentially saying that all the points in this side are going to get cancer, and all the ones on this side aren't, given the model's current data. But that threshold of where you set it is another parameter to set, right? So essentially now we've created another parameter threshold that we could set. You can make it 50% or argue about what the probability should be, but that's how it's used as a classifier. Okay, so that's that linear model for classification, logistic regression. So we can solve this just like we did with linear regression. We can solve this with these probabilistic parameter estimation methods. Do I have both? Yeah, so we have both. We can do it with MAP and say that we'll assume that the data is distributed as a Gaussian, and we're going to have the prior values for the mean and variance. So we define that, and then where does the sigmoid come in? One over e to x. Yeah. So now in this case we've got two functions, right? We've got our Gaussian function for the prior, and now we're going to do the same thing. We say argmax of this, and so we solve it, and we just expand it out, right? We use Bayes' rule, and we have these components. And then same way before, we don't need this because it's not dependent on the weights. The data doesn't depend on the weights itself, so we can drop it. And each part, we're solving the derivative. I'm looking for the sigmoid part, because the sigmoid in our case is it's that function, right? Because it's 1 over 1 plus ex exponent of y. I guess we didn't write it down earlier, that's why, yeah. So, yeah, in this case here, we got the prior is Gaussian, right? And then the posterior is sigmoid, right? And so we're combining those two together and replacing, and then reducing it. And solving this is basically the equivalent of doing logistic regression by using MAP. So you can't get a closed form for this, but they basically do search on weight. So if you've taken optimization courses, then you can kind of think about how you would kind of like propose different values of W and kind of take steps towards improving them. We'll do some gradient descent later when we do neural networks, so we'll kind of talk about that. That's kind of one way to represent it. But they put this prior on saying that the weights have a Gaussian distribution. But if you didn't want to put that assumption, you could do it with maximum likelihood approach. And so you do the same thing, except you're going to get to a different formula. So we've got our sigmoid function like before, but now we don't have p of the weights. But we end up with a simpler version, which, how does it compare? Which just gives us a different way to solve it. And it would basically, I guess, use a less, not biased, but influenced by any kind of knowledge about the underlying distribution of the data. It would just be learning it from the data itself. So there's different trade-offs for using these algorithms. So we'll talk about some of those in a bit. This is not, some of this can be more useful later, will make more sense later to come back and kind of think about how it relates to other stuff. We're going to talk about support vector machines with a different type of classification algorithms, a bit more complex, but actually logistic regression can be made to be quite similar to it, just by using a different way of representing this loss. So, but we'll talk about that when we get to SVMs. And then if you want to go to more classes, because this is binary, what we're doing right now, right? So you'd have to do something that takes into account many different x's. So these x's now are vectors, right? So that x is bold x. It's a little subtle to see, but it's actually multiple variables, multiple features. And so you have a set of weights, one for each feature. So you could still do that. You just have to have a function that can combine multiple values together and give you the same probability. So the softmax function is kind of generalization of that a bit, to say, take all the input variables with the weights and give me a probability, but you'd still use a threshold as a classifier for the same thing. And don't worry about this for now. Okay, so we can look up, I meant to look up a different, more of a set of them, but basically for all those kind of standard probability distributions, you can kind of pre-work out what the MLE formulas would be. Like we said, a lot of times it is just the mean of these variables, but depending on what you're doing, like for variance, for the normal distribution, it's not a direct average, but we can get a bigger list of those. So kind of trade-offs and knowing which one to use. MLE is, it's kind of like optimal in a certain sense if you have all the assumptions being valid, right? So if your assumptions that the formula distribution is known and it's the distribution that you gave it, it's the assumption that all the data is IID has to be there as well. I'm wondering why it's not on this slide. It also seems that your prior on the distribution of any parameters of there is uniform. So if you don't think the parameters of your model really are all equally probable, then you shouldn't be using MLE. You should be using MAP with some kind of bias. But if you don't know what it is, it's hard to do, right? So it's kind of, it requires a lot of knowledge ahead of time, but it has this ability, this nice part that is kind of, sometimes it's analytically solvable and you don't even have to do any learning. You just spit out the probabilities directly if you can get all the information together. So this one had some other facts about letting you, what's nice about them. This is more specifically to MAP, that if you have this prior knowledge, you can use it. It's also incremental, right? So as you get more data, you can kind of update your probability because you're using Bayes' rule. So once you have a probability distribution, you can kind of just renormalize the probability you have by the size of the data set so far and add the new data in and recompute it. So it's useful that way. Not all models let you add new data after the fact. And it gives you a probability distribution over data rather than just a yes or no answer for some class, so that makes it useful. And I guess, obviously, meta-classification, we're just saying that you don't have to just stick to one classifier, right? So you can ask the opinion of multiple classification algorithms about what the correct label is for your data, and that's fine. So these are ones that are easy to implement and try as a base case for comparisons. So MAP itself is usually harder to fit than MLE because you're giving it an extra restriction, right? You have to give it this prior, and so you're putting more restriction on it. It's got less freedom to fix it, to fit it. But if the prior we give it is uniform, then they're equivalent, right? So it kind of be pointless to do MAP if you give it a uniform distribution over all the variables, the parameters. So in that case, they're the same. And I guess I've never seen people talking about this too much, but if you have an infinite amount of data, MAP will get you to MLE. So it's kind of like a less accurate thing to do because you can get by with less data because you're giving it a prior, but it may not fit as well. In the long run, they should be equivalent, right? So, but that means that this one's faster to do because it doesn't need as much. It already has some information you've given it, which is this prior, right? It could also avoid overfitting. So when we talk more about overfitting again other times, right, by giving it this prior, you're saying, I know it's this shape. Don't go too far down one particular road because it's supposed to be Gaussian, right? Whereas MLE doesn't know anything about the data. It'll try to fit it whatever the data has, right? And if the data has a weird anomaly in it, it'll fit it, right? So that's the advice I saw somewhere, that you can combine them together, right? And say, do MLE on your larger data sets to give you the prior and use the output of this as your prior for MAP. And then you can do this more quickly when new data comes in. So that's kind of a combination you can do using these two methods. Okay. And then, right, I knew I had a slide on regularization. So we were talking about this a bit already, but if you want to improve it even further, you could add other regularizers on top, right? So if you know something about, like I said, you want the weights to not be too far apart, or you want it to be that, only a small number of the weights activate so that a couple data points can just tide the whole model, you can come up with a function, any function R, that kind of gives you a score that goes up when the thing you don't want happens. That's kind of going to penalize it, and it's going to make it move towards a model that satisfies your extra constraint, right? So this can also be used to help avoid overfitting because you don't want it to come up with some particular type of weights. Okay. So to give you then, so we've done k-nearest neighbors as a classifier. We've done